talk is given by Jesus Perez from CNRS on integrated polaritonics with zinc oxide and gallium nitride structures. Go ahead. Your talk is
Okay,
yours.
so thank you very much for the introduction. And first of all, I would like to really thank Dimitri and Guillaume for putting forward this virtual conference, which I think surprises most of us that it's going so smoothly up to now, and it's already a success just looking at how many people are connected. So yes, so what I would like to do in the next minutes is share with you some of the work we have been doing in the last 2 or 3 years on an integrated polaritonic platform based on zinc oxide and gallium nitride. By integrated platform, we mean what we want to do is to mimic somehow a silicon photonic platform. So what we would like is to create polaritons, generate polaritons in plane, modulate them, transfer them within the same chip, and then detect them. So yeah, before going on to the results, let me thank all the people that have contributed. So it's a very long-term collaboration between 4 different groups, and I would like to highlight the work of 2 PhD students, Geoffrey Crédet and Omar Jamadi, who is now postdoc in the group of Alberto Amo, and of Maxime Gromovy, who is a postdoc. So most of the work that I will show you today has been done by these 3 students. So yeah, before going into the polaritonic, for those who do not know gallium nitride and zinc oxide, let me remind you very quickly why they are interesting for integrated photonics. One reason is that they are transparent from the UV to the infrared, and besides that, they display both second order and third order nonlinearities that we can exploit in a very long wavelength range. So this is a very nice example from Tang's group at the University of Yale, where they show the supercontinuum generation from about 400 nanometers up to about 4 micrometers. And a second aspect, which is quite interesting in the field of integration, photonic integration, is the fact that these materials are both compatible with silicon. And this was nicely shown 4 years ago, where they achieved for the first time a CW room temperature gallium nitride laser directly grown or fabricated on a silicon substrate. So the nice thing is that we have demonstrated in the last years that a strong coupling and polariton lasing on silicon, it's also possible. So here we have the kind of vertical microcavity that we have been working on for almost 10 years. So we can use a zinc oxide or a gallium nitride active region. And here you see that if the quality factor of the cavity is sufficiently large so that polaritons have enough time to relax to the bottom of the lower polariton branch, we can get very nice textbook polariton condensation even at room temperature. So of course, if this worked, one would might think that we could use these vertical microcavities already for integration. And in fact, it's very easy to imprint some wave vector either by inclining the pumping laser, or as we heard yesterday in Pavlos Lagoudakis' talk, we can pump with a very tight, with a very small pumping spot, so that we have ballistic ejection. And we demonstrated that this ballistic propagation of polaritons can also happen at 300 Kelvin. The problem is that in this case, the wave vectors that are accessible are very small. So if you want with vertical microcavities to really propagate signals in plane, then you need either very large polariton lifetimes, and this can be only achieved in extremely high quality gallium arsenide microcavities, which is not our case. In fact, for the wide-bandgap semiconductor, the quality factor, we are limited right now in the state-of-the-art microcavities to about 5,000, which gives a lifetime in the, which is limited by the photonic lifetime in the order of 0.4 picoseconds, which should be compared with this 100 picosecond. So of course, the option is to go for a waveguide, and in fact, works on waveguided polaritons can date back to 2010 with this work on organic polaritons. But the merit comes back to the group of Sheffield of Maurice Skolnick and Dimitri Krystianowski, who revisited this platform. And in fact, they could demonstrate very large group velocities in the order of 50-40 micrometer per picosecond. But besides that, what is interesting is that this platform is much easier to fabricate, and in principle, it should enable to have an easier electrical control and injection. And what is very important, and I get this from this paper from Paul Walker, it's that they could obtain nonlinearities with a small number of particles and in a sub-millimeter length scale, which should be compared typically with millimeter scale for lithium niobate. So what I would like to share with you today, it's what we have been doing with zinc polariton waveguides. So I will show you that we achieve lacing, polariton lacing. But the main point I would like to focus on today is to show really that we have polaritons at the polariton lacing threshold, so that there is no doubt that we are in the strong coupling. And I will do this by showing the strong to weak coupling transition that we can follow up. And then if I have enough time, I will go to the perspectives to the ongoing work. So this is our system. So for this, let's say, proof of concept studies, we use the best quality that we can get. So we are employing a single crystal zinc oxide substrate, on top of which we grow by molecular beam epitaxy the optical cladding based on zinc magnesium oxide, and then very high quality single crystal zinc oxide waveguide. So the first question, of course, it's to answer it's whether we have or not polaritons. So to do that, we as the people from Sheffield did, we deposit silicon dioxide on top of our waveguide, and then we define some Bragg rating, so to outcouple the light which it propagates within the waveguide. And here we see this very nice polariton dispersion, so the strong curvature, and we can indeed get group velocities in the order of 10 to 25 micrometers per picosecond. So before going into the lacing regime, let me highlight one important point, which is crucial for what I will be discussing in the following slides. And it's the fact that due to the lattice parameter mismatch between the optical cladding, zinc magnesium oxide, and the zinc oxide substrate, and because of the crystal orientation that we are using, we have an anisotropic strain relaxation, and we have a tensile stress along one of the in-plane direction, and this create cracks, which hopefully for us they are parallel, since they are created along a certain crystallographic direction. And of course, these cracks play two very important roles. So the first one is that they play the role of outcouplers. So even without any grating, we detect some light. So this is a specially resolved micro-PL image where we pump here, and we see that polaritons are created and they are structured through this crack. And by finite element methods, we can simulate the outcoupling due to this crack. So we can map, for example, the extraction angle as a function of the photon as a function of the incident photon energy. But the most important role of these cavities is that they define a very nice in-plane mirror. So we have the refractive index contrast between the oxides and air, which gives rise to this very nice Fabry-Perot modes. So okay, we have the necessary feedback for a laser. So that's the next thing we did. And of course, the nice thing is that we have separation between cracks, which span the range between 4 to 5 micrometers up to 100 micrometers. So we can change very nicely the length of our cavity. So if we pump under quasi-CW excitation, so for 100 picosecond pulses at low temperature, we see here the appearance of this Fabry-Perot, so the onset of temporal coherence. And if we plot here the output intensity as a function of the input one, we see a very strong non-linear rise. And of course, this can be done also at room temperature. And basically, it shows the same kind of behavior. And of course, the only thing is that we have increased the lacing threshold by a factor of 5 to 10 times. And the question is whether this lacing comes from polariton gain. And of course, one might argue that in principle it should be very easy to detect this, because we can measure the dispersion, and that shows a very strong curvature. So we just need to follow up. But one should be very careful with these wide bandgap semiconductors with very large oscillator strength, because even in the absence of excitons, and this violet curve corresponds to the to the strong coupling regime, the orange dashed line corresponds to the same structure when we remove the excitons. And what you see is that there is still a strong curvature, and this strong curvature comes from the fact that there is a very strong band-to-band resonance, which is spectrally not so far from the lower polariton, where we expect the lower polariton branch. And of course, this applies to zinc oxide, and this also applies to gallium nitride. And we have made a very exhaustive study how to measure, how to determine quantitatively the Rabi splitting in such systems, which is not so straightforward. So this is a first issue, but there is also a second issue. It's how do we measure this dispersion? And of course, one should be careful, because we could in principle pump the cavity, the in-plane cavity in a certain region. We can in principle put our Bragg rating here so that we do not degrade, we do not couple too much light, otherwise the lacing threshold would increase too much. But of course, if we do that by construction, whatever will happen here, either in the weak coupling or strong coupling, it doesn't matter. Here, by definition, we will only extract polaritons. So just to be precise, so how do we do the next experiment that I will show you? It's the following. We will pump homogeneously the full length of the cavity so that all the cavity is under the same coupling regime. Then we deposit our Bragg rating all over the cavity. And of course, we design the structure so that the coupling is sufficiently large so that we detect light, but not too much to degrade the lacing threshold. And then what we do is we do a further spatial selection of the emission that comes from the center of the cavity, of the in-plane cavity, so that we try to remove as much as possible any contribution that could come from the neighboring or from the defining cracks. So if we now carry out this experiment, so this is what we see. So these are all dispersion curves as a function of pumping power, and what you see here is that we see a very nice this polariton dispersion when we are just 10% of the polariton lacing threshold. And what we also see is that, as I said, the bare cavity mode has also a strong dispersion. So one should be very careful. What we see now is that we increase the pumping power, and then we achieve lacing. So we see this very strong nonlinear emission rise, and what we see is that we have a dispersion which is very close to the initial one, and we can quantify it by assuming that the reduction of the oscillator of the exciton binding energy is corresponds to the band gap renormalization, and then we can quantify the reduction of the oscillator strength. So for at pumping at the threshold, we still have polaritons or excitons with 80% of the oscillator strength. And what is very nice is that we can follow continuously, so we can increase to 3 times the threshold, and we see still this very nice dispersion, which is clearly different from the bare cavity mode. And finally, at 22 times threshold, then we have a lacing in a certain dispersion, which in principle should keep 30% of the oscillator strength. But of course, one can argue that in this situation, it would be very difficult to differentiate the strong coupling or the weak coupling. So the nice thing with this experiment is that what we can follow the reduction of the oscillator strength in a monotonous function. And this means in practice that the transition from the strong to the weak coupling is very smooth. And this means that this mode transition in bulk zinc oxide, so we are dealing with a 3D system, it's smooth, and this is consistent with studies on bulk gallium nitride in the late 90s, and especially on the work on bulk zinc oxide, so no cavity, no waveguide, by Klimshin and co-workers that date back to 2000, but in fact they date back even to the 70s of the last century at the time of Benoit Laguillaume. So of course, this is very nice. We can do the same experiment at room temperature, and this is what we see. So again, at low pumping powers, we see very nicely the dispersion, which is far from the bare cavity more dispersion. We increase the pumping power, we lose some oscillator strength, but at the threshold we are still far from the very wave-guided mode. So we can be sure that even at room temperature we still lays under strong coupling. And then of course again one can continuously increase the pumping power, and we see that this transition is again smooth. And if you have look at the peak power, so in the previous slide we get a peak power to the transition to the weak coupling of about also 4 megawatt per square centimeter, and this means that there is a very weak temperature dependence of this mode transition, which is obviously compatible with the hypothesis that we did, that this critical mode density in zinc oxide is governed by bandgap renormalization, and this is again consistent with the works by Klinching and co-workers, and also by the works from EPFL, though these were corresponded to a gallium nitride quantum ones. So the take-home message is that this strong to weak coupling transition in edge-emitting polariton lasers that we illustrate here for zinc oxide. So as we increase the peak, the pumping power, so the peak goes from 100% oscillator strength to, let's say, 0% oscillator strength. It resembles a lot the transition that the group of Jacqueline Bloch in Paris illustrated in 2008 very nicely. And I want to look here. So this spectral shift is a continuous one, and there is no jump in the at the second threshold. And in fact, the second threshold, it's very difficult to observe in terms of intensity jump. And this is exactly what we observe in our system. So the transition from the polariton to the standard lasing regime, it's a continuous one. Okay, so we can now try to identify more similarities between this edge-emitting polariton laser and vertical polariton laser. So we compare here absolute polariton lasing thresholds, now mean, I express it in mean power. And what we see is that we have basically the same absolute polariton lasing thresholds. But this is only right if we compare these polariton lasing thresholds of the waveguide with a vertical microcavity, which typical characteristic time is comparable to that of the waveguide. And of course, for a vertical microcavity, the characteristic time it's defined by the quality factor, so by the photonic lifetime, by the photon lifetime. In our case, it's in the order of 0.4 picoseconds. And the thing is, what's the characteristic time for these edge-emitting polariton lasers? And then the characteristic time is defined by the time that the polaritons spend below the gain medium. So for this experiment, we use a 20 micrometer large pumping spot. And what we see is that at 5 Kelvin, we have polaritons that at the condensation that propagate at a group velocity of 13 micrometer per picosecond. And this means that these polaritons remain 1.5 picoseconds, which would be equivalent to increase our quality factor. And this is the reason why in this regime, we have a polariton lasing threshold, which is much smaller than the one on the vertical microcavity. What we see is that at 300 Kelvin, we get polariton condensation in more photonic-like state. So the group velocity increases. Then the time that polaritons spend below the gain medium, let's say the pumping spot, the reservoir, it's just 0.3 picoseconds comparable to our vertical microcavity. And what we see nicely is that the polariton lasing thresholds are quite similar. Okay, so these are similarities, but of course there is a very important difference between these two systems. So this is the vertical microcavity, and we have an absolute minimum where we can achieve polariton condensation if the quality factor is sufficiently high. In the case of this polaritonic waveguide, there is no minimum. There is almost a continuum of states where polariton condensation might take place. And then, of course, this, we have seen it in many talks since Tuesday. Since we have this minimum and we have repulsive polariton-polariton interaction, besides the screening of the oscillator strength, we see a small blue shift. And if we look now at this particular feature in our edge-emitting polariton lasers, we see that if we are close, so here to the the threshold, we see this blue shift. But since there is no minimum, if we increase in our pumping intensity much above threshold, then we enhance polariton relaxation, which accelerates the relaxation along this lower polariton branch. And then even if we have a local blue shift of the LPV, what we see is that globally, if we increase much the pumping power, so here we are 5 times above threshold, what we see is that there is a global redshift of the emission. And I think this needs to be highlighted because there has been some misunderstanding in the last months or years concerning this issue. Okay, so I still have 5 more minutes, I think. So I would like to show you some perspectives. So the first one is, I said we want to integrate several functionalities. So the first one that comes to our mind, it's obviously an amplifier. And this experiment, it's very nicely done with 2 coupled cavities. One will be the laser cavity. So we will pump above threshold this one, and then we will use the second cavity as an amplifier. And of course, we will look at the emission here. So if we pump this cavity above its polariton lacing threshold, and we observe here, we see these Fabry-Perot modes. If we now pump the amplifier below its threshold, what we see, it's an unstructured emission. And the nice thing is that when we pump this cavity above polariton lacing threshold and this one below, what we see, it's an amplification of the signal, of the polariton signal out here. And of course, we can have an amplification up to a factor of 50. And of course, we cannot go above, because if we pump harder, then we get lacing from this cavity. Of course, this is very nice, but this shows the limitation of our system, which comes back to the fact that we lie to have in-plane cavities, we lie on natural cracks. And this is nicely illustrated here. So here what I have plotted, it's the number of horizontal cavities in the same sample. As I said, we have the sample which is filled with cracks. And then we plot here the threshold of the polariton lacing threshold for all of these cracks. And what we see is that we have a inhomogeneous Broden distribution, so that obviously, if we want to make some fundamental physics study, or even if we want to make some technology out of this, we need to check every cavity. And of course, we don't want to do this. So we want to do 2 things. We want to push this distribution, obviously, to the lower lacing thresholds that we can. And of course, we want to narrow down this distribution. So to decrease the polariton lacing threshold of the waveguides, what we can do, so up to now we were using planar waveguides, so in infinite, let's say, transverse mode. What we can do is now we can pattern we can pattern waveguides so that we can decrease the number of transverse modes. So we can, I don't know if you see here, these bright lines correspond to the cracks, and these gray lines correspond to the patterning that we have done. And we go from multi-transverse mode waveguides to monomode waveguides. And if we now measure the thresholds here, is what we see is, we see let's say two sides in this graph. On the right, we see this decrease of the polariton lacing threshold when we decrease the waveguide width, which corresponds well to what we expected. But then, unfortunately, what we see is a strong increase of the polariton lacing threshold when we go to very narrow waveguides, and in particular to the monomode waveguide. And in fact, we understood this, and this comes from the fact that when we pattern our waveguides, we protect with some mask this part, but we do not protect the other part, as we want to etch it away. And what we see is that we degrade enormously the reflectivity of the cracks. And since for the narrow waveguides, the mode it's less confined, then we feel more the cracks which have been degraded. And in fact, if we measure now the polariton lacing threshold out of the waveguides, we have multiplied by 20. So what we have been doing in the last 2 years, it's working very hard not to rely on cracks, but rather to fabricate very nice vertical DVR. So this is now a gallium nitride based waveguide, where you see here in the zoom that we can pattern very nice vertical air gallium nitride DBRs. And the nice thing of these DBRs is, since we have a very strong refractive index contrast, we get a saturation of the reflectivity after 4 or 5 just DBRs. And here we see these very nice Fabry-Perot modes, and of course these cavities do show polariton lacing. And if you want to listen more about this, you just need to wait some minutes for the next talk. And for my last slide, I would like just to show you that after big efforts, we get now the first electrically injected polariton waveguide structure. So here we see one of these structures with just one, let's say, gallium nitride air reflectivity with the NMP context. And one very nice thing is that I show you here the diode characteristics, so the IV curve. And what it's very nice, it's that eventually we could even work at low temperature in the order of 200 Kelvin, which was not so, might not have been expected for gallium nitride, since the acceptor ionization energy is very large. But this means that we can sacrifice somehow the electrical injection if we need some temperature reduction for the polariton. So with this, I come to my summary. So I hope I have shown you, I have convinced you that we have in-plane polariton, edge-emitting polariton lasers, that we are working to integrate several functionalities on the same chip. We are trying to electrically connect this, and I had no time, but I would like just to indicate a very important aspect of this work is that we have shown that we have edge-emitting polariton lacing, and then we have revisited last year the phenomenology of our vertical microcavities. And in fact, if we go to close to a physical border of these microcavities, then we can see that we have competition between edge-emitting polariton lacing and the conventional, let's say, vertical polariton laser. And this, we think, it's very important, especially in the samples which are limited in size. And this typically applies, for example, for TMD materials embedded in vertical microcavities. And with this, I would like to thank you for your attention.
Thank you very much, Jesus, for that very nice talk. And now we have time for a couple of questions, short ones. Yes, Danielle.
Yeah, thank you. I'm curious about the cracks in your structure. So they are, I guess, they are naturally occurring and they follow the crystalline plane. But do you have any control on the distance between the cracks, or they are fully random? And also because they have to be oriented in the same direction and to be at the correct distance. So how do you control that?
Yeah, we have obviously no control at all. The nice thing is that okay, it's not gallium arsenide 1000, but you can imagine that because of the crystallography of this particular crystallographic orientation, these cracks can only happen in equivalent 100 plane. So they are naturally parallel to each other, and that's what allows us to have these very nice cavities. What I showed at the end of the talk, it's that obviously we can make very nice physics relying on these cracks, but we do not control. And what we want really is to push forward, let's say, the technology of these integrated polaritons. And now we have basically these very nice vertical air zinc oxide or air gallium nitride DBRs, which we control. So we can produce the same samples with no cracks. Then we produce the DBRs, and what we see is that we can attain much larger reflectivities than what we get with just one, let's say, zinc oxide air interface, since we now have a full DBR of zinc oxide air stack. So now we can have larger reflectivities and we can control them, and of course we can produce any length of cavity that we want.
Okay. We have time for one more short question and short answer. So, Peng Li has a question.
Yeah, nice talk, Jesus. So, yeah, I wondered for your amplifiers, it seems that you have 3 cavities. Your amplifier is also a cavity, and there is another cavity between the 2 cavities. So, how can you make sure that the amplifier cavity has the same mode energy of your lasing cavity, or you just get coupled modes from, if there are any coupling? So what kind of modes you actually get?
Yeah, so that's a very good question. What we think is that since we have such a very long cavities, we have almost a continuum of states. So because obviously one could expect some mismatch between the modes of each cavity that we do not control. But it turns out that it works for most of the cavities. So what we expect is that we have almost a continuum of modes. So any mode from one cavity could produce photons or polaritons on the neighboring cavity.
Okay, thanks. Yeah.
Okay, good, thanks. I think we move for the next talk, so thank you very much.